I think
Okay.
I said wrong was I had it the horizontal.
Standard form of the quadratic. There it is. This is your vertical stretch. This is your horizontal shift. This is your vertical shift. Okay? So you start with the y equals x squared function and you vertically stretch it. Okay? So here's your vertical stretch. You multiply every y value by a. If a is bigger than 1 and positive, that makes the graph taller and skinnier, right? And you can do that, we've done that with the table, and you should understand in terms of just a basic table from -2 to 2, what happens when you multiply your y values by some positive number bigger than 1. If you multiply by a negative number, then all your y values are going to go negative, right? Except for 0, which will stay 0. So the graph would go upside down, right? Now, if you add k to all your y values, that shifts everything k units. Up if k is positive, down if k is negative, right? And then if you replace x by x minus h, x values, to give you the same value of y, x values have to be h units bigger, right? Well, from the x-axis, h units bigger is h units this way, right? Now that's if h is positive. Now if h is negative, then I got to be. But that's why you have the horizontal shift. So what I do is I've taken this green graph, the y equals ax squared graph, the vertically stretched graph. There it is. Okay. Then I do k. I displace it by an arrow that has value k, right, in the vertical direction. Okay, we haven't talked about vectors. I put a little arrow over that because it is a vector and you might as well see the arrow. That's just a displacement of k units in the vertical direction, okay? And then a displacement of h units in the horizontal direction. I do that to the vertex, so I see where the vertex is going to go. And right now I know then that the vertex is at hk. Okay? Then the graph has to have the same shape because I've got to do the hk thing to every point. So you're going to end up, if you do the hk thing to every point, you're going to end up with the same shape. It's not going to be wider, it's not going to be narrower, right? So you just take that shape and move it so that its vertex is here, and there you've got your graph. Okay? So that's the fundamental thing you need to understand. Okay? And the other thing, just since we're in the summary mode, if you're in general form, you can find the axis of symmetry. I say add, I could just say is, because it's the line x equals negative b over 2a. Where's that come from?
From the quadratic formula.
Yeah, if you write the quadratic formula, the quadratic formula tells you two things. Zeros are at x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And, well, plus this square root gives you something to the right of what you get if you do minus the square root, right? Wherever negative b is, if you add the square root, you're going to add to that value. If you subtract the square root, you're going to subtract from that value. Right in between what you get when you add and when you subtract is your axis of symmetry. Because the axis of symmetry has to go halfway between your your zeros. Okay? So, we have this. The axis of symmetry is therefore just this. Now, whether you understand the halfway thing or not, understand that, have that picture in your head. Now, you can't have that picture in your head unless you know the quadratic formula. Okay? So, as I said last week, everybody should have theoretically come into class knowing it, but that's not going to happen. That didn't happen 50 years ago when we were in the whole space race. Okay? not even at the best schools, okay? So nobody really comes into this class knowing it. I mean, some people do, but everybody should be familiar with it. And since we used it back in January and have used it on occasion since, it should be reinforced by now. And as I said last time, come to class knowing the dang thing. I'm not going to test you on that today. We don't have time, but probably should. Okay, well, if you know the quadratic formula, then you know where to find the equation for the axis of symmetry. And if you understand what I just said, you'll know why that's the axis of symmetry. Okay? Well, in any case, that is the axis of symmetry. Vertex is at negative b over 2a, and then you plug in negative b over 2a here. And I could even write that. And you know, that's not something you want to memorize as a formula, but I'll write it out this way. Just to indicate that we plug this in to this, which gives us this expression. Okay? Now you don't actually write this expression out. You calculate it and then you put whatever number you get for this, because it's the same number here as it is here as it is here. If you've calculated the axis of symmetry, this is just indicating that you've calculated this number, it goes here and it goes here, right? Or it goes in for x, because that's an x value. It goes in, you plug it in for x, and you get this. And then the vertical stretch is A, okay? So, if you move 1 unit right or left from the vertex, the y-coordinate changes by A. Now, why is that? That's because if this is, let's say, where x equals 1, so here's y equals 1. If I vertically stretch by factor A, my y-coordinate for x equals 1 is going to be what? It's going to be A. Okay? In other words, the point 1, 1 is on the graph of your function, and the point 1a is on the graph of y equals ax squared, because if x equals 1, y equals a, right? Meaning then that if you go 1 unit over, you go a units in the y direction, right? Also, if you go 1 unit over to the left, you're going to go a units in the y direction by symmetry and by the numbers and everything else, okay? So when you graph this thing and you get your vertex, you know that if you go over 1 unit, you're going to go a units in the vertical direction and find a point on the graph.
Oh, okay.
Okay?
Now, it's still...
Now, if you can put that together and understand everything I said there, you got an excellent understanding of the graph of a quadratic and the general, or...
You're basically just saying the vertical stretch is still going to stay at A.
Yeah.
Even if you move it left or right, it's still going to stay at A.
Right. Yeah, it's because if you move left or right, well, if you move to -1, you're going to have a times -1 squared up here, right? So if you move to -1, you're going to go up to a. Now, this shape is the same as this shape. You still got the point 1a and -1a on this graph, right? And you maintain the shape, meaning if you move over 1 unit, you're going to go a units here. Okay? It wouldn't have the same shape if that wasn't the case. So that's something that's worth sorting out.